So welcome to another lecture on power system. So this should be your fourth lecture in already because the lecture 2 was too long. So in this lecture we're going to cover I think 2 topics. Okay, if you look from your presentation, there are 4 topics to be covered in this lecture, namely two-port networks, review of phasor concepts, and there are 2 transformations and symmetrical components. But the lecture, since we have too many things in this lecture, we are going to cover just 2 topics, namely the topic number 1 and number 4 in this lecture. Okay, so the two number 2 and number 3 are omitted. All right. As you saw from our previous lectures, that when we analyze the balanced or symmetrical three-phase system, okay, so for example, we have this kind of system. We have star connection between source. So this side is a generation G, and these are the transmission line T, and this is supposed to be your load D. Okay, so all these, the GTD subsystems are connected in star connection, or this is in German, it's called Sternschaltung. Stern means star. Okay, Schaltung means connection. Okay, so this is what we want in the three-phase connection, because as we discussed last time, that we would prefer to have our three-phase system to be connected in star or in Y connection. Okay, and the reason is that we want to analyze it in just one phase. Okay, last time we have derived that when the three-phase are when the three-phase are balanced. Okay, you can see that when the three-phase are balanced, there is no current flowing in the neutral. Okay, so we could remove the neutral current. And this is on the left side, the picture B shows you the single phase representation. So this is from the German textbook, so you would find a little bit different. Okay, but let me tell you that when the German textbook write the voltage drop like this, okay, the arrow is pointing downwards. It is like in English textbook, it is written like this. This is E, something like this. Okay, but this is a German text. So the current is flowing from source to load, and this is the voltage at the load is U. Okay, if I write in our common notation plus and minus sign, it should be like this. So the picture on the right side is a single phase representation. Okay, but in this case, this is the ungecoupled or uncoupling. Okay, uncoupling, meaning that each of these phases are the magnetic field or the electric fields of these 3 phases are not coupled to each other. So you could just consider one impedance without having the coupling effect between the lines. Okay, so this is the case of uncoupling. Okay, so the picture down below is written ungekoupled Dreieckschaltung. Dreieck in German, drei, you have learned it already, is 3. Dreieck, okay, Eck is corner. Okay, Eck means corner. So Dreieck means that it is in 3 corners like this. So it is a star connection. Okay, so this is a star connection. So when you say star connection, you see from this connection of the Z, all the 3 impedances are connected in star connection, or in German it's called Dreieckschaltung. Okay, you see that there is a voltage applied from phase A, B, and C with respect to the neutral. That would be the same as UA here, UA. Okay, the neutral is a negative side because this is the reference point. Okay, and UB is here. Okay, similarly UB is here, and this is a UC. Okay, and the situation if the systems are balanced is that we could, you know, we could transform, right? In the last lecture we have transformed this the delta connection into the Y connection. You remember that if we have to transform the delta load to the Y load, the impedance just reduced by 3 times. So you can see that this is the results of the transformation from the star to from delta to star. Okay, this is the equivalent circuit that when we deal with star connection. All right. So this is the case of uncoupling. You can see that if there is a coupling between the lines, and in this case you can see when the current is flowing into the line, there is a magnetic field surrounding the lines. Okay, so meaning that the magnetic field surrounding the line A with due to the flow of the current IA, okay, that would induce also in the line B and line C. Similarly, the current flow in B would have the magnetic induction between itself, I mean surrounding itself and between other two phases. Okay, this is called the mutual coupling. So this is the notation M. M would stands for the mutual inductance between two lines. Okay, if we take this coupling effect into consideration, okay, and we write the KCL or the voltage difference between the sending end and the receiving end, you can see if you write the voltage drop across the phase A from sending end on the left side to the receiving end on the right side, the voltage drop in this case, you can see that it's an effect of the current flowing not just in the phase A itself, but this is the voltage induced by the current in phase B and the currents in phase C, right? This is these two IA and IB and IC terms are the voltage induced due to the mutual coupling or the inductive coupling from phase B and C to phase A. Okay, this two term is the voltage induced due to the current flowing in phase B and C. So this kind of phenomena is called coupling, right? This is called coupling effect. Okay, this is called the coupling effect. So since this is if the systems are balanced, you see that if the system is balanced, the IA plus IB plus IC is 0. So IB plus IC is negative IA. So you can replace this, because if you assume that the mutual inductance are to be the same between phase A to B, B to C, and A to C. Okay, so all these mutual inductance are the same. So you could take this the common factor of j omega m out, and this would becomes IB plus IC, and the IB plus IC is negative IA. So you can put this as the total inductance. So you can see that incorporating the mutual coupling between the other lines, the inductance of the line just reduced by that the mutual inductance. So if you can see that if you don't consider the inductive coupling, so you don't have this M term, okay, that would be in general case. I mean, you can just do the normal the uncoupling case, right? So now you could also see from the capacitive coupling. In this case, if you consider the capacitive coupling, you could also do the same thing. Okay, the capacitive coupling is the capacitance. We will learn it later because the capacitance is a result of the induction between the two running to the current running conductors. Okay, so there is capacitive coupling between the lines and also the coupling with respect to the neutral as well. Okay, so if you take all this into consideration, you could see that normally the capacitance that we when we model the line, right? We model the line, we just do this Z0. These are the normal capacitance. You see that when we say about capacitance, you have to say that it is with respect to the neutral or to the ground, right? So these are the capacitive coupling between the lines. So if you have the coupling effect, you can see that your capacitance will increase by 3 times, right? The 3 CK. These are due to the coupling. Okay, and I think just to give you the quick review. Okay, and we will touch on this when you learn into the transmission line chapter, right? This is a new concept. Probably if you haven't learned from any other class, you will learn it just now. Okay, this is the concept called two-port network. The reason I introduced this to you is that when we consider a power system, okay, we have seen from our previous example that we normally we are interested, right? We are normally interested in the voltage and the current at the receiving end and those of the sending end. Okay, so you could see that we are talking about two quantities from two ends. Okay, both from sending end and the receiving end. So by talking about two-port networks, okay, the two-port network we normally we are interested in two sides of the network. Okay, when we mean network, meaning that it is not it's not necessary to be the closed path. Right, so one end we will put it as a sending end, or this is the source. Okay, and the other end would be the receiving end, or this could be the load. Okay, so, and on those two ends we are interested in both the voltage and current. So these are the current, or these are the variables that are of our interest. Okay, so the concept of the two-port networks will allow us to deal with most of the situation in power system where the current and the voltage are of our interest. And you also know that from last lecture that since we are talking about power system, so the most prominent variable that are of our interest is the power. So you could see that knowing this U and I, or voltage and current, okay, you could derive for the power. Okay, you could if you know the phasor, if you see these are these variables comes with the underscore, means these are the complex numbers, right? So if we put U times I2 conjugate, you get S2. Okay, S2 is U2 times I2 conjugate. So this is the complex power at the receiving end. So you could analyze active, reactive power, anything. Okay. So when we are talking about two-port networks, we normally, we are interested in this matrix called. This is in German, but I will explain this to you, of course, in English. But the situation that we are looking in power system is divided by this matrix called in German Ketten matrix. Okay, or if I have to say in German, we call Ketten matrix. Okay, Kettens in English is called chain. Okay, it means change, chain matrix. Okay. Why is it all chain matrix? Okay, that would mean that this is a matrix that would link between the variables from one end to the other end. Okay, because the chain means that you are tying something by a chain. Okay, so from this picture means that we are interested in U and I. Okay, and the arrow of this picture indicates that the U2 and I2 are going into the network or going to this box, meaning that U2 and I2 are inputs. Okay, these two are inputs. Okay, knowing this U2 and I2, we could compute U1 and I1. So if you say in terms of mathematics, okay, these U1 and I2 are independent variable. Okay, this is an independent variable. Okay, these are independent variable, or if it is function, this becomes input. Okay, because knowing this, you could compute this one. Okay, look at the arrow of these two. Okay, so this is become dependent, or if it is a function, this becomes an output. Okay, because knowing this, you could compute this. So that would mean that why it's called kitten, because it is tying up between the set of two variables from one end to the other end. So the equation is like this. Okay, knowing U1 and I2, you could compute U1 and I1 by multiplying this with a matrix. Okay, this is something like a transfer matrix. Okay, so this matrix itself is called kitten matrix. Okay, it's called kitten matrix. All right. Well, I would just run through this all the possibilities, and then we will do one example to show you, right, how the two-port network works. Okay, so if we are trying to link between U and U means the voltage and the current. Okay, this is the relationship of this is called admittance matrix. Admittance in English. This is called admittance in English. So admittance is the Y, right? Y is the inverse of Z, right? V is equal to I times Z, or you simply write C times I. C is a parameter of the network. So in this case, you know I, okay, and you want to find V. So I is your input or independent variables, and V is dependent variable, right? So if you change, you divide by Z on both sides of the equation, so you get I is equal to 1 over Z times V. So this guy is called Y, or admittance. Okay, in this case, you know V, you know voltage, and you want to find the current. Okay, that's why we need the transfer matrix called admittance matrix. Okay, so in this case, it's simply straightforward. You have inputs or independent variable as voltage on one end, and you want to compute the current as an output. Okay, so look at this equation. You see that we know the U, you multiply by this matrix, and then you could compute I. So this matrix itself is called admittance matrix. Okay, this is called admittance matrix. So the admittance matrix, okay, I will not go into the detail how to transform from the kitten matrix, or this is a chain matrix, to the other form. But if you want to look for the derivation, you could go to any circuit textbook, and you will see it from one of the derivations. So the book that I'm using is Alexander and Sadaiku. If you are interested, okay, how to transform this matrix to matrix of this form, okay, you could check, okay, circuit textbook. Okay, I would recommend you check the circuit textbook yourself, such as Alexander, okay, Alexander, and Sadaiku. Okay, you can check this one yourself. Okay, so I just run through the other two the other types of the two-port networks. So if it is an hybrid, an impedance matrix first. Impedance from last slides we have V is equal to Z times I. So in this case you know the I and you want to compute V. Okay, you want to this is wrong. So you have to. I'm sorry. This is the admittance matrix. The equation is here. So I'm sorry. So meaning that you know I and you want to compute V or U on the other side, right? This is the corresponding term. And if it is called hybrid matrix, okay, hybrid means that it is mixing between U and I from one end and the other end. So you could see that in this case the input is U1 and I2, okay, knowing U1 as an input, and I2 as an input to the box. So these two with the arrow pointing into the box, these are the inputs. So these two are the input to this hybrid matrix, and we want to compute U2 and I1 out of the box. All right. We will go to the example. Okay. We don't have any. I don't want to put this as a separate clip, so please take the notes yourself. Right. I will just go to the whiteboard over here. Okay. This is from Alexander Sadaiku example. You have to, maybe we will write down this together. So this example 19.8 from Alexander Sadaiku. Okay, Alexander and Sadaiku. Textbook chapter 19. Okay, we have a circuit like this. Plus minus 3I1. We have two ports, right? One port, the port 1 is on this side, I1, and if we are putting the current going into the port, okay, going into the port as I2, okay, and this is the V2, right? This is 10 ohm, 20 ohm, okay, okay, and in this case, all right, the problem asks you to determine the matrix that would link between V1, I1 on one end, and this is what is the matrix over here. If we know the input of V2, I2, okay, V2, I2, right? So the matrix that we use to explain this is something like this: V1, I1, okay, and V2 on this side, V2, okay. From this definition from the book, okay, this is just a definition from this book. You have to look when you see, okay, the book says is A, B, C, D. We want to find the A, B, C, D. This is a constant, A, B, C, D, okay, and the direction of the current, okay, since we are interested in this way, the current is flowing, okay, from this end towards the network and going to the other end. So in this situation, this could be sending end of the system, and this could be the receiving end of the system. So the current just flow from source to the load. So the I2 is here, okay. So but the current given in the picture, I2 is pointing, okay, the I2 is pointing towards, going to the port here, okay, going to to this end here. So the I2 here is negative of this guy here. You can see this is a different direction. Okay, knowing that the current flowing from this direction and this directions are not the same, so we have to put in a different form. Okay, simply, you know, the I here is negative of this I2 here, so please be careful with this. Okay, I will put this as a negative over here. Okay, I will just put this negative, because if you see from here, this is V1 is a linear combination. V1 is equal to, okay, A times V2, right, minus B times I2. Okay, and I1 is what? Is C times V2 minus D times I2, right? So I just changed the sign of the current in this case. Okay, just change the direction of the current. Now we want to see, if you want to find the matrix, I mean we want to find the parameter of ABC, we use the definition. All right, you can see that if you want to know these two first, these two, A and C, okay, you know the A is what in this case. If I want to find the A in this case, I will just set the I2 to be 0. Okay, if I2 is to be 0, I can get the A is equal to V1 divided by V2, right? This is only true when your I2 is 0. Okay, similarly, C is equal to what? C is equal to I1 divided by V2 when I2 is 0. Okay, now you can see it's true, right? When I2 is 0 means, in this case, your circuit on the receiving end, on this side, the port 2, the current is 0 means it is open circuit. Okay, so you can see that the parameter A and Z can be computed when, okay, can be computed when port 2, or I would say this is receiving end. I want to use this term, you know, to get you familiar with the term in power system. Okay, when port 2 or receiving end is open. Okay, it's open. Oh, sorry, it's open. Okay, you can analyze the V1 and I1, right? The ratio of V1 and I1 to the V2. Okay, and you can see from here as well that when you want to find B1 and B and D, okay, your B is what? Maybe we just change the color. B is what? In this case, B is V1, right, divided by V2, and you have to put negative, right? This only true when your, oops, sorry, this is your, oops, I made a mistake, right? Did I make a mistake? So in this case, I2, oh, I'm sorry, it's true. When V2, okay, is 0, and the D here, okay, the D which is here, right, this column here, the D would be your the ratio between I1, okay, negative of I1 divided by V2, okay, divided by V2 when V2 is 0, right? When V2 is 0, correct? So that means that these two parameters B and D can be defined when port 2 or receiving end is short. Okay, when there's a short circuit at the receiving end. All right. So let us consider the circuit. Okay, the circuit is here. Okay, if we put the circuit, okay, I'll just put the circuit here, right? Oops, sorry, I'm not get used to this. Okay, okay, just oh, it's not going with me. Oh, never mind. Okay, should be moving. Never mind, I just write it here, right? Now you see, we want to compute the A and C first when the I is 0. So this is this is the scenario already, right? When there is no voltage, I mean the port C is 0, port 2 is open. So meaning that we put the voltage source over here, and this is open. We want to find the ratio between V and I, right? In this case, if you want to find the A, we want to find the ratio between V1 and V2. Okay, so you can see, since there is an open circuit right here, right? The current I1 is flowing this way, and the current I2 is, since this is open circuit, there is no current in this case. The I2 becomes 0. Okay, so what is the V1 here? The current flowing from the source and come back to the load in this way. So the V1 is 30, or this is the 10 times I1, and the current I1 is flowing down below, so this is 30 I1. Okay, the current the V1 is 30 times I1. And by the way, what is what is the current? I mean, what is the voltage drop across this one here? Okay, the current flowing through this is an I1, so this would create the voltage difference. I mean, the voltage drop across this 20 ohms equal to 20 times I1, right? Because this is the same current flowing around this loop. Okay, so what is V2, by the way? The V2 here, you put the KVL around this, right? So when there is an open circuit, it doesn't mean that the voltage drop across this is 0, right? But you know that when you open this terminal, the current is 0, but the voltage is non-zero. Okay, so in this case, you see the V2 would be, you put the KVL around this. Okay, you get 20 I1 plus 3 times I1 is equal plus V2, right? Plus V2 is 0, so your V2 would be 17 I1. Okay, so your right, so V2 is 17 times I1. So what we are looking for is the ratio between A is the ratio between V1 and V2, right? So you can answer straight away that the V1 over V2, right? V1 over V2 in this case is 30 over 17. So this is A, parameter A in this case. Okay, 30 divided by 17, right? What about the parameter C? Okay, your C is, you see the C it's computed from the circuit with when the receiving end is open. So the I2 must be 0. So this is the circuit, right? I2 is equal to 0. This is a circuit. So the ratio between I1 and V2. So I1 and V2 is from this equation, right? So now you could see that the okay, I1 divided by V2, okay, I1 over V2 is 1 over 17, right? 17. So I1 over V2 is what? It is C. This is a constant C. So you could answer the parameter C in this case. Okay. So this is a circuit when the terminal 2 is open. Okay. So we have answered this A and C already. Now we are left off this B and D. Okay. So B and D can be computed when your circuit is short on the other end. Okay. Now I will rewrite. We apply the voltage at V1. Okay. Because we need to know V1 and I1. Okay. I1 10, 20 ohm. Sorry. And this is the dependent source plus minus 3I1. In this case, the I2 is here, and this is a short circuit, so you know that the V2 is 0, and the I2 is flowing this direction from right to left. Okay. So in this case, we are interested in the ratio of V1 and V2, I1 and V2, right? So how would you compute this one? Okay, now you see that the current I1 is flowing in this direction, and the current I2 is flowing to this direction. So KCL at this point, right, okay, results in the current flowing from the top node to the bottom node. This is I1 plus I2. Okay, you know the current flowing into over 20 ohms, right? Now you could see that the voltage drop across this 20 ohms, if you know the current flowing is this much, so the voltage is what? Is 20 times I1 plus I2, right? This is the voltage, right? So now you could do the KVL around these two loops. Okay, you do the KVL around these two loops. Okay, you have minus V1, okay, plus 10 times I1, which is the voltage drop across this, and plus 20 times I1 plus I2, but this is equal to 0. Okay, this is the KVL around loop 1, and you can see the current the KVL around the loop 2. Okay, the positive, the arrow of this is pointing to positive sign of this voltage source. So this is 3 times I1. Voltage here is 0. So you enter this negative sign of this 20 I1 plus I2 equal to 0. You have two equations, equation 1 and 2, right? So you have these two equations. Okay, so now you have to manipulate the equations a little bit. Okay, so now you could see that the this term, okay, for this loop 2, right, you could do, what you could do is that you need to find V1 and V2. So the it would be the nice idea, you know, that if you want to find the B, in this case, you have to eliminate this. If you could eliminate this term 20 times I1 plus I2, okay, because you know from the second equation that this term would be equal to what? To 3 times I1, right? 3 times I1. Okay. Now in this case, okay, you could rearrange the equation a little. You could rearrange. Did I make a mistake? Oh, I'm sorry. This is wrong, right? V2 is 0, so you have to put. I'm sorry. This is divided by I2, so you have to change this divided by I2, right? This is wrong because when we set V2 to be 0, okay. I'm sorry. This is not right. Okay. If we put into this, okay. Oh, if you put something like this, so you don't have any, you don't have the relationship, right? Because you want to map the ratio between V1 and I2, so this cannot be replaced by 3 times I1. Okay, so you have to change from the equation 2. So the equation 2, we have to write the relationship how much the I1 is in terms of I2. So this is minus 17 I1 minus, okay, 20 I2 is equal to 0. So I1 is what? It is negative 20 divided by 17 I2. Okay, so this is from 2. This from 2 you have to put this into equation 1. Okay, so put number 3, so you substitute 3 into 1, substitute the equation 3 into 1, so you get minus V1 plus 10, right? This is, I'm sorry, this is not 10, because you have to substitute. We have 10 here and 20 here. This is 30. This will become 30. I1 is minus 20 over 17 I2 and plus 20 I2 becomes 0. So in this case, okay, you could solve this. Okay, V1 is equal to 15.2941 I2. Okay, let's check this one yourself. So V1 divided by I2, it's B, but you have to take the negative sign due to the different direction of the current I2, right? So the B is negative of 15.2941. Okay, this is the B, right? So we could answer the B. So the D is ratio between I1 and I2. I1 and I2, this case here, I1 and I2, we could answer from equation 3. Okay, I1 and I2 is negative 20 divided by 17. So the D here is what? It is negative of this ratio. So you could answer 20 over 17. So this is the answer, right? Okay, so this is the answer. All right. So the nice things about this, the two-port calculation is that when you know the voltage and current from receiving end in this case, right? So because we need to map the relationship between receiving end and the sending end, meaning if you could derive for the transfer matrix like this, okay, voltage and the current on the receiving end, okay, you just multiply by this transfer matrix, and you get the sending end quantities in this case. Okay, so this is the benefit of using the two-port networks, right? So let's go back to the slides in this case. So this is a calculation. We are talking about the application of the two-port networks to compute the voltage drop and power loss. So this is just an example. Okay, and towards the end of this, I have an assignment for you. So you should do this and return it back to me. All right. Given a network matrix like this, so we know the relationship between you and I on sending end and receiving end. In this case, you know the two sides, which is the receiving end, and you can compute the voltage and current on the receiving end. So you can see, if you define the relationship or the ratio between the voltage at the sending end with respect to the voltage at the receiving end, or the ratio between U1 and I1. So remember, this is the ratio of the voltage at the sending to the receiving end. Okay, you see when there's a if you put the source, okay, you transfer the power to the load, and this is your load. Okay, the voltage at the source is generally is more than the voltage at the receiving end. Okay, so the K is the ratio between these two. So it means that if the K is 1.02, what does it mean by this? It means that the voltage at the source is 2% higher than the voltage at the load or at the receiving end. Okay, this is the interpretation. Okay, so you can see that when we determine the U1, the relationship between U1 and U2, the ratio of these two, so it can be written in terms of the complex form like this. This is the K e to the j of a certain angle. Okay, so this angle is called in German it's called Spannungsdrehung, phase shift. This is a phase shift. Okay, the voltage phase shift between just a phase shift between sending end and receiving end. Okay, the shift between the sending and receiving end. So you could see that U1 and U2, how could we derive for this? You can see U1 is if you see from here, this is a multiplication of this line and this column. Okay, it is A11 U2 plus A12 I2, right? And this is a K1, this is a U1 here. Okay, if you want to find U1 divided by U2, or if it is in German, it's called Durch. This is the divided by U2. So you divide by U2 on both sides of the equation, U2. So in this case, you see U2 and U2 just cancel. Okay, this is I2 divided by U2. This is the reciprocal of Z. Okay, so you can write this in terms of 1 over C. Okay, 1 over C. So the C here is the the ratio of U and I and U, right? In this case, okay. So this is the called driving point impedance at port 2 or at the receiving end. Okay. In this case, it is a certain, this ratio it's a certain vector, all right. If we define, right, if you draw if you draw the phasor diagram of U1 and U2, you could see what do we mean by this. Okay, now you could see that U1 is equal to U2 times K. Okay, you can see from this ratio U1 is equal to K times U2. If we put U2 as a reference, right, we multiply this by K. K is e to the j of a certain angle, and with, of course, with some gain or some magnitude. So this is a U1. So okay, this is the shift it's called phase shift because it's shift from the receiving end by this angle here. Okay, and in this case, if you want to see, right, how much is the voltage drop or how much is the voltage difference between sending end and the receiving end, okay, the voltage drop, or it is in German, it's called Spannungsabfall, okay, falling. You can see if it is in English, it's fall. You know fall, right? Fall, right? Spannungsabfall, voltage drop. Okay, drop is to fall. It's the same as to fall, right? You can see that this is the difference between U1 and U2, right? And the voltage drop is here. This is an epsilon, right? So the epsilon itself, it can be defined in terms of the K, okay, of the K factor as well. Okay. As I said earlier, knowing the relationship of U and I, you can find the power, of course, right? Since you could compute the voltage drop, okay, you deal with the voltage. If you know the relationship of the current, you multiply these two and you get the power loss. So in the next slide, we also do the same thing with the ratio between the current, okay, at the sending end and the receiving end, I1 and I2. So you know that this can be derived from the network matrix, right? I won't do this for you. Okay, you could check this yourself. You multiply. You see the multiplication of the row 2, then you get this relationship, right? So if you know if you want to find the Ks, this is the ratio of the power from sending end to the receiving end. So this is in terms of the ratio of power at the source and at the load, right? That is the you know, it's a multiplication of the U and I conjugate, right? So in this case, it is a multiplication of the K. This is a complex, okay, complex ratio of the voltage times the complex conjugate of the K, or the gain of the current conjugate, okay, because this is in terms of the complex power, okay. Now you could also see that we put the K at this form, and this is the K conjugate. Multiplication of these two results in some you know, it's a complex number, so it is this can be written in terms of the magnitude and the some angle, okay. So mathematically you can see that S, okay, Ks is here. The S1, okay, is the same S1 as Ks times S2. So knowing S2, you could compute the S1. This is an idea why we use a two-port network, right? As we discussed earlier, that you know, the quantity from one end, you multiply by something, you multiply by a certain gain or certain matrix, right? You get the quantity on the other end, okay? So you could see, if you happen to know the S2 at this point, because you see S2 is a vector, okay? S2 is defined by what? It is P2 plus JQ2, active power at the sending end plus J reactive power at the receiving end, okay? And your S1, which is the sending end power, right? Complex power at the sending end. It is what? It is the multiplication of a certain gain and with the rotation, right? With the angle of rotation by delta. So the S1 is here, okay? So if you if you project this S1 on the real axis or on the horizontal axis, this is P, right? You know that projection of S on the horizontal axis or the real axis is an active power, and the projection of S1 on this axis is Q1, right? So this one is P1 and this one is Q1, okay? And similarly, if you if you decompose this component of S2, okay, S2, you get this one. This is P2, and decompose this S2 over here. This is Q2, right? So you can see that the difference, okay, you can see the difference between Q1 and Q2, P1 and P2. So these are the losses, okay? Because the Q is a source and the port 1 is a source, and it's loose, right? It is lost in the line, okay? It's lost in the line, appear to the load at this much Q2, which is less than the quantity at the source. So the difference of these two is called power loss, okay? PV, V in German, this is German. Verlust is loss, okay? PV, V would stands for Verluste, but in English you would write P loss and Q loss, okay? P loss and Q loss, okay? P loss and Q loss. So it can be computed, okay? This is just an equation. PV, QV is a P1 minus P2. This is this much. Some, P2, which is the P at the receiving end, because you see we know the quantity at the receiving end. All right, and there's a multiplication. So why we use two-port networks? Because we need this, this kind of multiplication. We need this kind of factors, right? So we can see that we could map in this case the power, okay, the quantity is at the receiving end, which is the P2 and Q2, to PV, sorry, this is German, PV and QV, all right? So in this case, you could see from these two equations, this is the benefit of using two ports. We put PV, QV on this end as a dependent variable, multiplied by a certain gain matrix, and since we know the power at the receiving end P2 and Q2, right? And this is a matrix. So the matrix of which is, it's coefficient of these two lines. So this is the matrix, okay? So this is the benefit of using two-port networks. So I hope you would appreciate this, the concept of two-port networks in the first part of this lecture. So don't forget to do this question and turn it back to me whenever you finish watching this video, and we will see you in the next section of this lecture on symmetrical component. Okay, thank you.